All right, hello there. This is the binary search tree project. As we can see, it was created by me, Chris Moskovic, for CS3 382. And starting off with, we'll do a quick demonstration of the code, and then we will actually run through it. So if we run the code here, on this left side, we can see we have the in order traversal as well as the maximum value. Then we also have the in order traversal after deleting the number 6. So we can see between 4 and 7 is 6, and it is no longer there. And then we also have some more rigorous testing as the bonus performance analysis of this binary tree with implementing 100, 1,000, 10,000, and 100,000 nodes for the insertion time and deletion time. And then we actually do get a nice little graph here as well with the deletion time being this orange line and the insertion time being the blue line. So when we get up to 100,000 nodes, we can see that looking at the data as well, uh, the times go up. And then for the first two, just 100 and 1,000, it's pretty light work. And we can zoom in and see that for those first two, it is going to be 0 seconds. But then once we get to 10,000, that's when it starts to jump up a little bit. All right, well, now that we've seen this program in action, we'll do a quick run through of the code. Now, starting off with, we're going to have a tree node that we use to for the binary search tree. This is the actual like tree itself. Or sorry, that's not the actual tree. That's just for the tree node. Um, but then down here is the actual binary search tree. I have a comment that says we use a class instead of a dictionary because we want to be able to modify the left and right child nodes, which are these down here. As we can see, left and right. That's for the insertion. And then as we go through this class here, we have the constructor here, and then we have the insert function for inserting a node, which calls, if you see here, the insert recursive function. So this makes sure that we're not inserting any kinds of recursives. Now, we also have a way to delete a node, as well as a recursive helper function for making sure we're not deleting any kinds of recursive things, or sorry, so that we're not deleting the same node twice. And then this up here is for that we're not inserting the same node twice, or child. Moving on, we also have a way to find a node in the binary search tree, as well as a way to find the maximum value in the binary search tree. And then we also have a way to find another node, find min and find max. And as we can see, for the min, it goes to the left. So this is focusing on those left children. And then for the right, we're focusing on the right side, which is the max. If we actually run it one more time real quick, we can see down here that we are doing in order traversal. So that means that the min is on the left side and then the max all the way on the right. Moving on, now we get into some of the example stuff down here. So this first one is just an example with that original, just standard input array hard coded in, and then we insert the numbers and just do some traversal as well as finding the maximum value and then deleting and looking at the traversal afterwards. Now this next part is my favorite. This is the actual testing where we get to do measuring time like this first function here, which created that really nice graph. We got to see the time it took to implement these programs or to implement the amount of nodes, sorry. And to do that, we do a little sneaky trick where we get the start time, which is time.time, so that'd be like the actual computer time. And then we call whatever function that is, and then the end time is time.time. And then from there, we do end time minus start time to figure out the total runtime of the program. Next up, since the binary search tree is sorted, we want to generate random values, and we generate them in the range from 1 to 1 million because we want to avoid duplicates as much as possible. So in this function, as you can see, we are for, sorry, in range n. So that's going to be uh, up here. We do in n just for returning the amount of random integers that we then assign to a node. So we have node counts here. We have 100,000, 10,000, and 100,000 that we use for testings. And then we have a list to store the items of insertion and deletion times. And then next up, this is the actual testing of the times. So for n in node counts, so we have n in node counts up here. We generate a bunch of random values. Then we have assigned the binary search tree to BST, which then we insert all the values with another for loop inside of the original for loop for inserting all those random values. And then we also want to make sure that we're measuring with time here. So we use the lambda function to insert those uh, amount of nodes, and then we also delete every single node as well. Now down here, we just display the data table as you saw. We have the data table here, and then what just showed up was the plot. So we're using matplotlib, or the matplot library, to then actually graph it so you can visualize it. But yeah, that's all. That was just the original binary search tree function with the bonus performance analysis. I hope you enjoyed and have a great rest of your day.